So I've almost told you everything you could ever wish to know about OpenACC, and possibly a lot more than you wish to know at the start of this. But in this final talk, it's just a bit of rounding up of a few things and a little bit of a view of where OpenACC is going in the next version. OpenACC, you can do as much as you want to do. It's a complete programming model. But there are cases where it's useful to be able to interface with other GPU programming models and other things that's going on. Why would you want to do this? Well, if you're using libraries in your code, if you're running dgems and BLAS libraries, you don't want to rewrite that on the GPU. You want to use a library that's on the GPU, and you want it to process data that's on the GPU. You might want to call CUDA kernels from your code, again, without transferring data back to the CPU in order to do a CUDA memcopy. You want to be able to run CUDA kernels processing data that's already there. And you might want to use some sort of streamlined communication path which lets you send data directly between accelerators. And in order to do this, all of this requires being able to expose where in the GPU memory this data lives, which the compiler has usually hidden this information. And that's what the host data directive is. And I talked about it a little bit yesterday, but it's probably worth saying it again. Usually with OpenACC, the compiler, the runtime, is handling all of the creating the arrays that you need on the GPU and where they live and freeing them at the end. And so when you want to call these libraries, if you want to do something external that's outside of OpenACC, you need that information to be made available. And that's what host data does. So basically, you've got an OpenACC data region. Well, of course you have. That's how you got your array onto the GPU to start with. Now that this array is on the GPU, so you're within the ACC data, ACCN data, within there, you would like to process this data on the GPU in some way. So you need, within this data region, you want to say, I'm calling something, a library call, a call to your own CUDA kernel, a call to NPI. But when you tell in that call and you pass as an argument the array that you want processing, you don't want, that code obviously is a CPU executed line, and normally the arrays that you pass would be pointers in CPU memory. You want to say, for this particular region of the code, I want this to be a pointer in GPU memory. And so this is what the host data region gives you. So why would you want to be able to interoperate with CUDA? Well, there's two reasons. One is that you want to get some better performance. You've ported everything with OpenACC. There's a particular kernel where if you could use some particular feature of CUDA that's quite low level, but it would really benefit your application, then you really want to be able to call a CUDA kernel. But you don't want to rewrite everything in CUDA just to do that. But it makes sense, in the same way that there's still applications where particular routines are done in assembler, because you can just do it very fast using assembler. And you want to be able to link that computation into the main program. And the other reason for this might be that there are some core kernels in your application which you maybe already have a CUDA version that's very highly tuned. You might be able to redo it in OpenACC, but it would take a lot of tuning work, a lot of investigation. But you don't want to do that because you've already got that CUDA kernel and you're happy using that CUDA kernel. But don't then go and say, well, to port the whole application, I've got to rewrite everything else in CUDA. Maybe do that in OpenACC and make use of these CUDA kernels that you've got. So I showed a quick example yesterday about how you would do that. So basically, you call a routine to double the values of your array within the data region. It's a call on the host, but it's inside a host data region. And I'm saying, when I talk about array A here, I don't mean in CPU memory, I mean in GPU memory. And this call, this CUDA wrapper, which just accepted this pointer in as an argument, it's just a pointer. C code doesn't care, you give it a pointer. and then it just passes that pointer straight in for the kernel launch. And so that's the example that I showed yesterday. What you do need to be careful of is that you need to make sure that any OpenACC stuff has finished before you start the CUDA kernel. So there's a CUDA synchronize in there, and I need to make sure this kernel has finished before I return to the main program, so I've put a CUDA synchronize there. I could have alternatively had ACC wait statements in the Fortran or the C code. But what I don't have is CUDA mallocs, CUDA memcopies, CUDA frees, and whatever going on, because the data is being used already on the GPU. I've talked already about streamlined communications. If you want to get the data to move directly from the GPU to another GPU using MPI, what you do is you put the MPI calls and you want to pass in a device, a GPU memory pointer as the send buffer rather than a CPU memory pointer. So basically the code looks exactly the same as it did on the CPU, except you put the host data region around the MPI call so that the buffer A will now be an address in GPU memory. And what happens is that the MPI library will look at that pointer and it will use the unified address space magic, unified virtual address space of CUDA, of the GPU, to say, aha, this pointer is something in GPU memory. I will do something different because I know that the data is on the GPU and it should move directly from the GPU over the PCI into the NIC and away. So the host data is used there. And the other thing is to do with calling libraries. Because if there's libraries, use them. Because, you might be able to do better than the library writers, but you'll have to work very hard. I mean, one example of libraries, Cray has their own accelerated library called libsci ACC. Well, if you're American, you call it libsci ACC. If you're on this side, you call it libsci-ACC. But this provides some libraries. They do some clever stuff in that you can use them in a sort of hybrid way where they can use CPU or GPU or both, depending on the situation. If you're doing it within an OpenACC program, you're probably not using them in this hybrid way. You're probably using them strictly, the data's on the GPU, I need to process data on the GPU. So if you were doing this and you just had code on the CPU, you would call dgem, and that dgem, because you've got the libsci module loaded, it resolves that this is inside the libsci library, and you've got some data A and B are combined in order to give you the result C. So you've got, these would be pointers in CPU memory. Now, the Cray, if you do this with the libsci-ACC and you're just using CPU code, the library does try to do clever things and say, well, how big are these arrays? How long will it take to transfer them? How fast will they go on the GPU relative to the CPU? Oh, they're quite big. It might actually be worth shifting these to the GPU and doing them and sending them back. It might be faster than doing a dgem on the CPU. So even though your code is pure CPU, it is magically using the GPU under the hood in the cases where it's efficient to do that. So this has nothing to do with OpenACC. But what this does mean is that you should be very careful. If this module is loaded and you're compiling CPU code, there is potential for the compiler to pattern match your dgem calls, and the GPU is being used. So if you're trying to profile your code and understand CPU performance, you should not have this the accelerated libsci module loaded, because the pure CPU code performance can change because it's using the GPU under the hood. But if you're doing it with an OpenACC code, what do? You say, well, I've got my data array, data region here with some data arrays, and there's stuff going on, processing here, processing there. I'm going to call dgem. I need the accelerated version of dgem, and I need to process data that's already on the GPU. So here's a host data region. I call dgem A, B, and C. So it looks very like the CPU code. We've got the directives in, obviously, but we're calling the accelerated version of dgem. We don't need to do that. What you do is you do this. You have your data region, you have your host data, and you just have A, B, and C. The library will look at A, B, and C and say, these are device pointers. They're GPU pointers. They're in the GPU memory. You don't need to call dgem_ACC unless you want to. It will use the accelerated version of dgem because it's realized that these are all on the GPU. So again, that's a sort of minimal change to your code because it still looks exactly like the CPU code, except for the directives. Now, a big topic of the standard, if you look in the little folder thing you get there, is the Runtime API. And this is function calls that you can make in your code that allow you to do OpenACC types of things. So directives were comments in the code that are ignored if the compiler doesn't like OpenACC. These calls are library calls. They're part of openacc.h, the include file. And just like OpenMP runtime calls, these would be library calls that are still there if you switch off OpenACC recognition. So if you really want your code to compile both on the CPU and the GPU and you want to use the runtime functions, you will have to pre-process random. And they give you some finer grained control. My advice here is that all the examples we've seen have not used the Runtime API. You don't need to use it in the first instance. The control that it gives you, in many cases, is replicated by directives. Or, if you're running on something like a Cray XK system, it's not relevant. So there's a lot of things about what sort of devices do I have, how many of these different sorts of devices do I have, and which device will I use next. And I better get that device ready to use, or I can shut down that device because I don't want to use it anymore. This is kind of, you've got some sort of cluster where you've tacked on a number of different GPUs of different types onto your system, and you're going to kind of try and manage to use OpenACC running on all of these different ones. This is not relevant to a Cray system. You don't need to do it. You don't need to init and shut down the GPU on a Cray system. It's done for you automatically. There's one GPU per node. It's a very easy to understand hardware model. So unless you're working on something quite strange, you probably don't need to worry about these. You might want to use the ACC init. With the Cray library, Cray compiler, you don't need that. It's done automatically as soon as it starts. If you're using other compilers, you may want to call ACC init as the first line of your program to get the GPU going. And then, otherwise, what happens is the first kernel you hit, this initialization will be done, and you'll notice that this first kernel seems to take 5 seconds when you expected it to take, a few hundred milliseconds, because there's 5 seconds of getting the thing up going. So if you put an ACC init call right at the start, you remove that initialization time. As I said, the Cray runtime does that automatically. Other things you can have, for more very advanced users, you can have some much finer grained control of how memory is allocated and freed on the device by using runtime calls. You are really starting to get away from the idea that your code is the same but with a few directives when you start to do this. There may be cases where there's a reason to do it. The API that you're most likely to use is the stuff to do with the asynchronicity. So just like there was a wait directive to have all the asynchronous things finished, you can call a runtime function. And just like you could wait for a particular stream of tasks to finish, there's a function that you can call that will do that for you. Why is there an API call and a directive to do the same thing? I think it's down to preference more than anything else. I mean, there's no real reason to use one over the other. One thing that you can't do with a directive is to test whether this stream of tasks has finished. And if it hasn't finished, then you're free to go off and do something else. So there you might use the API call, because that's the only thing you can do with the API that you can't do with directives. Cray also has some extended runtime API calls. This is stuff where there's kind of non-standard stuff you might want to do, very advanced control of device memory. Some of the stuff will be in OpenACC version 2, So it was sort of, a vendor extension to version 1 that will be in version 2. Some of the stuff is in there. There are places where you could use it, but if you do that, then you have to be aware that you're doing something that's specific for the Cray compiler. If you want to see what you can do, well, you can look at these man pages, and they will give you some more information on those functions. So what's going to happen in OpenACC version 2? I have no idea if I'm allowed to talk about this, but I will anyway. A technical report was issued at Supercomputing last year. They're now finalizing version 2 of the standard. There's been I think the big decisions have been made, and there will be a formal launch shortly. Shortly means in the next few months. So what are the proposed additions? Well, there's default none, unstructured ones. I've got slides on these, so let's just go through the slides on each of them briefly. If you're a C programmer, and especially a C++ programmer, the idea of data regions in your main program and you know that the data will be available here, it's globally visible, and it will live, and then it will, at the end of this, it will disappear. If you're using constructors and destructors, it just doesn't work that way. You don't have this globally visible data. You just know that data is created in this call, and it will be destroyed in that call. How do you get a data region to get that data onto the accelerator while it lives? The idea is to have, instead of having ACC data and then in the same part of the program, same main program or whatever, end data, in the constructor you would say something like enter data, and in the destructor you would say exit data. And the data you'd have to mention what this data was, and when it reaches the matching end thing, it would disappear. So it would give you the ability to no longer have to have formal data structures. You would have data structures that are much more flexible. Version 1 of OpenACC does not let you do calls inside accelerator regions. Everything has to be inlined by the compiler or by hand. Compiler is better, but it's hard to understand what it did when it's inlined all this code. The user doing it is bad because it destroys the call tree. And it also limits the use of third-party libraries. You can't call a GPU library from within a kernel. So the idea with the new directive is that you would be able to have much more, it limits the use of third-party libraries in that you don't know what those library functions might be called. The routine directive will provide a much better way to manage calls without having to inline. Another change that you can see a sort of immediate use for is the idea that, it sounds a bit strange to begin with, is that the wait directive is asynchronous. So you would launch a wait, but then you wouldn't wait for it to wait. You could wait on your wait later. But why would this be useful? Why this is useful is because sometimes you want to do something like, when you've finished updating the main array, I would like you to separately pack buffers in the X direction and the Y direction for halo exchange. Now, normally what you would do is you would have to do a wait to finish updating the main array, and then you'd do a separate launch to pack, and with that separate launch, you would overlap packing the X buffer, packing the Y buffer. What would be much nicer is just to launch off all in one go, update the main array. When it's done, separately, in parallel, do the X buffer and the Y buffer. With the async clause in version 1, you can't do that. You can say, do that buffer, and then, do the main array, then do that buffer, and then do this buffer. But you don't want to do that. You want to overlap the two buffers. So you kind of want to have more of a tree structure to your dependencies rather than a linear structure. And this is what this would do. So you would say, launch a kernel to update the bulk array. Then you would say, and when this has finished, you should do the X array. You should pack the X buffer and send it to the host. And all of this is asynchronous, so the CPU is immediately ready to get to here, and it says, and when S bulk is ready, when you've finished updating the bulk, you should do the Y buffer, but this is a different handle to this, so these two sets of tasks can overlap. And then you're free to go away and do a lot more independent host computation if you want. And then you can wait to complete all of this tree of tasks as opposed to this single string of tasks. So it's kind of, it sounds, when you start thinking about this, you think it's very strange, but then when you, it's the sort of saying, and when you finish doing that, you're going to have some other things to do in parallel. And so you could change, by doing that, you could, instead of having a synchronization point in here, this all flows now in one big asynchronous stream of tasks. And if you had something else to do on the CPU down here, you'd be free to go away and do it. And you'd have, without having to worry about synchronizing midway. Nested parallelism, why can't you have a parallel region inside a parallel region? The idea is that you would be able to nest them. Obviously, you wouldn't move data on the inner one, but for hardware that supports dynamic parallelism, you might implement it in that way. For hardware that doesn't support it, you would have to do the inner kernel serially, which would be pretty poor performance, but it would still execute. And some more API calls that basically replicate these new directives. If you've looked at anything to do with the cache clause, you know that you have to tile the loops in order to make the compiler know exactly how much data in shared memory it's going to need to use in order to cache the data. At the moment, if you look at the examples in the Cray man page, it's a bit of a hack because it uses all sorts of Cray directives to tile this loop nest. The tile clause will come in, that you'll put it on the loop directive, and you'll say the next two loops should be tiled, and you can optionally say what the tile size should be, and then schedule that. So that will make using the cache clause a lot more standard. What things still need to be done? Deep copy. Dynamically allocated arrays in C are a mess. Well, not a mess, but it's very difficult, and it's the way you have to end up doing it is quite non-standard. This needs to improve, and this is being worked on to improve. The same thing happens with Fortran-derived types, although Fortran tends to be a bit more defined as to how things work, because you're not just passing around pointers, you've got array descriptors. Better use of not having to inline stuff and using dynamic parallelism. That's partly addressed in version 2. As I said, multi-dimensional arrays need to be better handled. The async system is improving now. I mean, this ability to go to a more task-based dependency tree instead of simply streams of tasks. Dealing with non-contiguous memory is a problem. Moving some of the extended runtime routines, the ones that are really useful, you should really have directives to do some of this work. And support for multiple devices is not something that the Cray compiler has really had to deal with so far. So in summary, OpenACC is a way of porting codes with hopefully minimal changes and hopefully pretty good performance. What to take away? There's a lot of information, but if you want to take away, what should you do? You do ACC parallel loop to accelerate the loop nests. You do a data region to reduce the data movements. If you get both of those going, you're doing really well. You'll probably see things starting to go faster. If you want to start tuning, look at the number of threads per block with the vector length clause and look at collapsing multi-dimensional loop nests. But only when you've got rid of the data transfers. So it's the 3 acts, accurate. Make sure you've got checksums. Check it's right at every stage. You don't want to get to the end and it's wonderful, but it's wrong, but you've made 5,000 code changes to get to that point. Accessible. Make sure the data is in the right place. That's your biggest performance boost. And accelerate. Do the kernel optimizations at the end. But please ask for help. CSCS does have some of the world experts in using OpenACC. Cray can help you as well, again. So please ask questions. Things that work. How do I do this? Why doesn't this work? Should I be able to do this? is there a way around this? Just ask questions. We're happy to help. So in the spirit of OpenACC version 2, we'll exit the data region at this point, but not exit delete. You must take it away with you. Thank you. So I will have to leave around lunchtime, so if there are any questions, please grab me to talk about things. Otherwise, please email, get in touch if there's anything not clear. The slides should be going up. And if you are using OpenACC, we are very interested to hear what problems you're having, in the sense of, we really need to do this, we need a way to do this, or we need this to be supported better because this doesn't work. We're very interested in this. Cray is having a big internal meeting in the middle of March where we're prioritizing what users need. But to do that, we need your feedback. So please